So hello everyone and welcome back to another video. And today in this video, I'm going to build a neural network with backpropagation. So the first thing I want to talk is I want to define what's backpropagation. So backpropagation is a process involved in training a neural network. It involves taking the error rate of a forward propagation and feeding this loss backwards through the neural network layers to fine tune the weights. So this is the definition of backpropagation. And I'm going to complete the whole code in Google Colab and it will be written in Python 3. And if you want to download the source code with all of the explanations and comments, then check the link in the description. So the first thing we are going to do is we are going to import random and import math. And we are going to make a class called neural network. We are going to define the learning rate at 0.5, which is pretty standard. Everyone does that. And now the first thing we are going to do is we are going to initialize a neural network object with given parameter. So let's initialize a neural network. Self inputs non-hidden. I'm also going to explain this line by line. So just let me write it first. Layer weights is equal to none. Forward the bracket, comma. Hidden layer bias is equal to none, and output layer bias is none. Output layer bias is also none. The self dot inputs is equal to num input. So what this statement means, this is the number of inputs for each input layer neuron. Now, the second thing we are going to do is we are going to create a hidden layer as an instance of the neuron layer class. And with the num underscore hidden neurons and bias value initialized to the hidden layer bias. So self dot hidden layer num underscore hidden and hidden layer. This is just the beginning, so please watch. And now we are going to create an output layer as an instance of the neuron layer class with num underscore output neurons and bias values initialized to the output layer underscore bias. Let's do that. Self neuron layer, and this is going to be num output and output layer bias. Now let's initialize the weights from the input layer to the hidden layer neurons using the provided hidden underscore layer underscore weights or random initialization if none is provided. So let's do this self dot init underscore weights inputs to hidden layer neuron. This is hidden layer weights. Once we have completed that, I'm also going to initialize the weights from the hidden layer neurons to the output layer neurons using the provided output underscore layer underscore weights or random initialization if there is none. So self dot init, and this will weights from hidden layer neurons output layer neurons, and this is going to be output layer weights. So moving on, we are going to create a new function, and it is going to be we are going to just call it def init hidden layer neurons. We are just going to copy this, paste it right here, and then self hidden layer weights. So now we are going to initialize a variable to keep track of the current weight index. So it is going to be weight, and we are going to just leave it to 0 as for now. Once we have done that, we are going to iterate through all the neurons in the hidden layer. So for iteration is for h in the range, then self dot hidden layer dot neurons. Now we are going to iterate, sorry. Now we are going to iterate through all of the input neurons. So iteration through all of the input neurons. So self that num underscore inputs. And if there are no provided hidden layer weights, assign random weights. So if there are no hidden weights, we are going to assign them something or completely random. If not, hidden layer weights, self dot hidden layer dot neurons, h weight dot append, and this is going to be random dot random, cool. Otherwise, assign the provided weight to the hidden layer neuron. If this is not the case, then we are going to assign the provided weights. So self dot hidden, this one layer. And once we have done that, we are just going to increment to this. So this number keeps on getting to 1, then 2, then 3, then 4. So now we are going to just increment it to, so weight num plus is equal to 1. So what does this function do? This function initializes the weight between the input and hidden layers of neurons in a neural network. It takes two arguments, and which are self and hidden layer weights. So it will take two arguments. The self argument refers to the instance of classes where the function is defined, while the hidden layer weight, it assigns random weights to the connection between input and hidden layer neurons. If there are provided weights, it assigns those weight to the connection. The function also increments the weight index for each connection to keep track of which weight is being assigned. So this is the first function. Now let's create another function, and let me just copy that. This is another function. Copy. We need to take care of all of the intention, and there will be two arguments. Output layer weights. Now the first thing we are going to do is we are going to initialize a variable to keep track of the current weight. And then we are going to iterate through all of the neurons in the hidden layer. So the output layer, the neurons. After that, we are going to iterate through all of the neurons in the hidden layer. For H range. Sorry, what? If there are no provided weights to if there are no provided output layer weights, then we are just going to assign it to random. Otherwise, we are going to assign the weights which have been provided to us. And then we are just going to increment it. If not, output layer weights. Dot neurons, else cell dot output display layer dot neurons weights dot append. Then we are just going to weight underscore num plus equal to 1. So what does this function do? This function initializes the weight between the hidden layer and the output layer neurons in a neural network. It takes two arguments, self and output layer weights. The self argument refers to the instance of the class where the function is defined, while the output layer weights is an optional list of weights to be used instead of random values. The function iterates through all the neurons in the output layer and then through all the neurons in the hidden layer. If there are no provided output layer weights, it assigns random weights to the connection between hidden and output layer neurons. If there are provided weights, it assigns those weights to the connection. The function also increments the weight index for each connection to keep track of which weight is being assigned at the end. So that is what this function does. Now we are going to create a function which is going to print the structure of the neural network. So once let me write it down and then I will explain. I will also go through each point when I'm writing it down. So function, we are going to name it inspect self. So first thing we are going to do, we are going to print a separator. That's enough. And then we are going to print the number of input neurons. So number of it is going to inputs. And this to get the data dot format self dot inputs. After that, we are going to print the separator again. So this print the separator again. And after that, we are going to print a label for hidden layers. So hidden layers. And after that, we are going to call the inspect method on the hidden layer object to display its details. So display details hidden layer dot inspect, and we are going to get another separator, and then we are going to print a label for the output layer. So print a label for output layers. This is for output layers, and then we are going to call the inspect method on the output layer object to display details. So this is going to be self dot output layers dot inspect, and let's just print the final separator. So what this function do? The function inspect. So this function inspects and prints the structure of a neural network. It takes one argument, which is self, which refers to the instance of the class where the function is defined. The functions print information about the neural network, including the number of input neurons, hidden layer details, and output layer details. The inspect method is called on both the hidden layer and the output layer objects to display their respective details. Separators are printed between each section to improve the readability so that everything doesn't become too much congested and everything's remain all right. Now we are going to create another function which is called feed forward, and in this cell inputs. So now we are going to pass the input values through the hidden layer and get its output values. So hidden layer outputs cell dot hidden layer dot feed input. And after that, we are going to pass the hidden layer outputs through the output layer and get its output value. So we are going to return self dot output layer dot feed forward and then hidden layer output. So what does this function does? And this functions perform the feed forward process in a neural network. It take two arguments, self and input. These are the arguments which is going to take. The self argument refers to the instance of the class where the function is defined, while input is a list of input values. The function first passes the input values through the hidden layer by calling the feed forward method on the hidden layer object. This method returns the output values of the hidden layer neurons. Then these hidden layer outputs are passed through the output layers by calling the feedforward method on the output layer object. The final output value of the output layer neurons are returned as a result of feedforward process. Now we are going to make another function, which is we are going to just call it train. So def train. So for training, this neural network is going to use online learning, that is updating the weights after each training case. So training inputs, training outputs. Insert, feed forward, training inputs. So the first thing, output neuron deltas, PD output. This is going to be 0. I will explain once I have written everything. Self dot output layer dot neurons and for 4 in the range in self dot output layer dot neurons. And now we are going to assign the total weights for this. And again, I forgot this. That is going to be alpha E and beta Z. I will explain what that means in a bit. Outputs, neuron, total, and that is 0. 7 dot output layer dot neurons. This is going to be O, and this is also going to be O, non-zero. And then dot calculate really total training outputs, and this is going to be O. And once we have done that, we are going to get the hidden layer deltas to dot hidden layer deltas. So PD hidden total net input, and this is going to be 0. Hidden, so for hidden, there dot neurons input h in range of neurons. And now we need to calculate the derivatives of the error with respect to the outputs of each hidden layer neurons. What hidden neuron output, and this is going to be 0 for O in range neuron WRT hidden HIDEN double DEN hidden neuron output incremented by PD errors output. I know it's looks a bit complicated, but let me just finish it. Then I will explain it to you line by line. Output layer dot neurons 0. Weights, and this is going to be a H. All right, everything look good, no error. And then PD errors WRT hidden neuron total. So dot hidden layer dot neurons, and this is going to be H. Dot calculate PD total net. Now we are going to write another one that is for 3 and update the output of the neuron weights for O in range. Save dot output layer dot neurons. This is O the weights and then semicolon. Holy shit, this is very long. I didn't thought that, but we are coming to an end. We are just writing it to train. We are updating everything, and after that, we are going to create a function where it is going to calculate the errors and the final back propagation, and that's it. We are done. So bear with me for a few more minutes. PD. Calculate. And then self dot output layer dot neurons O dot weights W underscore O minus equal self learning rate PD WRT wait. And now for the fourth and final part, we are going to update hidden neuron weights with 4H in range self dot hidden layer dot neurons H dot weights W also IH in range self dot hidden layer dot neurons weights feeding hidden neuron total net input H self dot hidden layer dot neurons H dot calculate PD total net RT weight W underscore IH. And the final line of the source code is hidden dot layer dot neurons H dot weights, which is W underscore IH, self dot learning rate, and this is PD, error, WRT, and weight. So this is a very long function. So what this function exactly do? So bear with me because I have got a very long explanation because I typed for very long. So this function trains a neural network using an online learning method, which is updating the weight after each training case. It takes three arguments, which are self, training inputs, and training outputs. The self arguments, the self arguments refers to the instance of the class where the function is defined, while the training input and training output are a list of inputs and outputs value for a single training case, respectively. The function performs the following step. Step 1. Calculate the output neurons delta, partial derivatives of error with respect to the total net input. It is for this one. Using the calculate PD underscore error, where is it? Calculate PD underscore error underscore WRT underscore total under net. You can see it. It's very long. Method of the each output neuron. After that, it calculates the hidden neural deltas, partial derivatives of error with respect to the total net input, using a combination of the calculated output neuron deltas, output neuron weights, and the where is it? Calculate PD total net input WRT weight input. And after that, we are just going to update the output neuron weight using the calculated output neuron deltas and the calculate underscore PD underscore total net input WRT weight method of the each output neuron. The learning rate is multiplied by the partial derivatives of the error with respect to the weight to determine the weight update. And finally, after that, we are going to update the hidden neuron weights using the calculated hidden neural deltas, which is calculate PD total net input WRT weights method. So everything works fine till now. If I run this, I'm going to see a lot of error. That's why I'm not going to run this. Now we are going to write a function which is going to calculate total error, and this is for self and training sets. First of all, initialize the total error at 0. This is going to be 0. And then we are going to iterate through the each training set, which is len training sets. And then we are going to unpack the training inputs and outputs from the training set. Training output is equal to training sets, which is P. And then we are going to perform a feed forward pass with the training inputs. Feed forward pass with training inputs. And after that, we are going to iterate through in range. We are going to iterate through each training output. Len training outputs. And now we are going to calculate the error for the current output neuron and add it to the total error. So total underscore error is plus self dot output of neurons. And this is O. Calculate error training. O. And then we are just going to return our total error. So what this function does? So this function calculates the total error of the neural network for a given set of training data. It takes two arguments, self and training sets. The self arguments refer to the instance of the class where the function is defined, while training underscore sets is a list of training data, which with each element being a tuple containing the input and the output values for a single training case. The function iterates through each training sets, performs a feed-forward pass with the training input, and then calculates the error for each output neuron using the calculate underscore error method. Where is it? This one. The total error is incremented for each output neuron and returned at the end using the return total error method. Now we are going to make what do we call it? A neuron layer class. So class neuron layer. So the first function we are going to make it is we are going to initiate it init self neuron bias. So every neuron in a layer share the same bias. So self dot bias is equal to bias else random dot random. And then after that, I'm going to initialize the neuron list and create neuron instances with the shared bias. So self dot neurons is this for I in range num underscore errors neurons self bias. Once we have completed that, I'm going to create another which is function inspect. This is going to print the number of neurons in the layer. So we are going to print all of the neurons in the layer self neurons for I in range print neuron which is n. We assign it to n. And now we are going to print the weight of each neuron in the layer. So for printing weight, W in range, then self neuron. We're going to print the weight. So neuron and the weights. It is going to be W. And then we are going to just print the bias of the layer. So print bias, self bias. After that, I'm going to create another function which is called feed forward. And this is going to be self inputs. And we are going to pass the inputs to each neuron in the layer and collect their output values. So outputs is empty for neurons in, sorry, for neuron in self.neurons output dot append calculate output input, and then we are just going to return the outputs. And the last function is definitely called def get output self. And this we are going to collect the output values of each neuron in the hidden layer. So this is just to collect the output. So output is empty for neurons and self.neurons. Dot append return out. So what this entire class neuron layer does. So the neuron layer class represents a layer of neuron in a neural network. It has the following attributes. The first one is init, init, which contains three arguments: self, neurons, biases. This is the construction initializes the layer with a specified number of neurons and a shared bias. If no bias is provided, a random value is assigned, which is this. After that, we got ref, the function self-inspect. This method prints information about the neuron layer, including the number of neurons, weight of each neuron. This is to print the weight of each neuron, and the shared bias, which is this one. And then we got feed forward. It takes two arguments, self and inputs. This method performs a feed forward pass by providing the input values to each neuron in the layer and collecting their output values. And after that, we get outputs to the self. This method returns the output values for each neuron in the layer. Now for the final part, this is going to be, let's make another class neuron. This is the final part. After that, we all can go home. Self bias. Let's initialize the neuron with a given bias. So self bias, self your weights. This is weight. After that, let's calculate output. Input. We are going to store the inputs and calculate the outputs by applying the activation function to the total net input. Self dot inputs is input, self dot outputs is slash self dot calculate total net input, and then return the output. After that, we are going to create another function called def calculate total net input, and this is going to be self. This is to calculate the total net input by summing the products of the input and their corresponding weights, and then after that adding all of the biases. So total is 0 for I in a range one self dot inputs total self dot inputs, and then we return total. Now we are going to create a function to apply the logistic function to squash the output of the neuron, and the result is sometimes referred to as net2 or net1. So let's make a function called the squash input. Now it's done. Now we are going to determine how much the neuron's total input has to change to move it closer to the expected output. Now that we have the partial derivatives of the error with respect to the outputs and the derivatives of the output with respect to the total net input, we can now calculate the partial derivatives of the error with respect to the total net input. So we are going to create def calculate PD error WRT total net input, and this is going to be served and target output, and then return calculate PD WRT output. Circuit calculate PD total net input WRT input. And now we are going to calculate the error for each neuron is calculated by the mean square error method. Def calculate the target output return 0.5. After that, we are going to create the calculate self dot output, and then we are going to create the calculate PD total net and self return self dot output, and this is going to be 1 minus self dot output, and then that calculate PD total net input WRT weight self dot index return self input index. Now it's done, and let's just write the last method, which is, for example, it's a very short one. We are not going to define neural network, which is 2 by 2 by 2, and then hidden a layer weights are 0.15, 0.2, 0.25, 0.3, and then hidden layer bias is 0.35, output layer weights are 0.4, 0.45, 0.5, and 0.55. Output layer bias is going to be 0.6 for I in the range 1000, and then dot range 0.05, 0.01, 0.001, 0.99. And then we are going to take number round, calculate total error. Now let's run this.